Folks, I'm going to take you through a couple of questions. Both of them have kind of intricacies that make them a little challenging. This first one is about three different objects that interact at various times. All right, it's really about two object interactions. There's a person. There's this 65-kilogram person. There's this snowball, and there's this other person. I'm actually going to identify those as three different masses. That says 65. M2, 0.045. M3, 60. Okay, and so let's talk about what happens. Well, the 65-kilogram person throws a snowball. So that means there's an interaction between the snowball and that person. All right, then the snowball flies through the air and hits the second person. So there's a second interaction between the snowball and the second person. That means there's two different interactions that happen here. And for that reason, I'm going to talk about the interaction involving the other person later. For now, I'm going to talk about the interaction between the snowball and the first person. Because if this person throws a snowball, it means initially the person was holding the snowball. So these two objects kind of start as one combined mass. And actually, notice here in the problem, the statement of the problem, it tells us that the first person is initially moving forward. So it means that these two objects are sort of doing this, moving along together. All right? And they do that until later, some later instant, let's see, clone, when they break apart. So I'm going to draw my little delineation here between before and after. So before, they're moving like this. I'm going to call that the initial. Later, snowball gets thrown, V2 final here. And then the question is, well, what happens to the person? I'm going to say, like, there's a V1 final. I'm assuming it's to the right. Probably is. I guess our answer will tell us. So let's handle this part of the interaction first. Well, this is a two-object interaction, right? Any multi-object interaction, the principle to apply is that momentum is conserved. All right, so I start that solution looking like this. There's a total amount of initial momentum. There's a total amount of final momentum, and those are equal. All right, and then we say, well, I'm going to jump right to this. Here's the first object's initial momentum. Here's the second object's initial momentum. Here's the first object's final momentum. The second object's final momentum. Now, because of this kind of intricacy where a person is holding snowball, what you can do in a case like this is say that two objects are moving at a common initial velocity. But then at the end they are separate, M1, V1 final plus M2, V2 final. And the thing that I'm looking for here is, notice, we haven't even defined what we're looking for yet, but I know this is true. This statement is true. All right, but notice we're looking for what are the velocities of the people after the snowball is exchanged. Well, the first part of the exchange is person one throwing the snowball. So I want to know what this person's speed is after the interaction. So algebra says to solve for V1F, first I've got to undo the fact that M2 V2F is added. So now watch this. I'll even change my notation a little bit. Watch this. M1 and 2, the initial, minus M2 V2F. Well, that equals M1 V1 final divide. Boom, look at how quickly I wrote that. I wrote the substitution in of all those values in there. Notice, here's our mass of the combined person snowball system, right? Here's the speed system was moving at. Here's the speed of the snowball relative to the Earth. Here's only dividing the first person's mass, and you get what you get. I get V1 final 2.48 meters per second. Now, notice I got positive 2.48 meters per second, and the whole time here I've called it, well, I called this velocity positive, I called this velocity positive, and what I'm really saying is that this direction is positive, and therefore my positive answer means 2.48 meters per second in original direction is the best I can say. Okay? Okay. Now, the second part is, well, kind of picks up where this part left off, right? And that is that, well, now the snowball, let me do this, the snowball, now moving at this speed, groupity group, now comes and whack, bumps into this, bumps into this, come here you, bumps into that other person. All right, so we've got to handle the interaction of snowball, boom, sticks to, we assume sticks to other person. Get over there. Where did this one come from? Now, the thing is, what we have called so far V2 final actually becomes like a V2 initial for this second interaction. You get that? I'm going to call this V3 initial 0. The person, this person isn't moving, just sitting there. All right. So this is the big, kind of a big deal in this question, which again isn't the most standard. Well, you're not always asked about these two interaction situations where, well, something's final circumstance becomes the initial circumstance of a different part of the question. But that's what we're doing here. All right. So for object 1 and object 2's interaction, this is the final speed. But for 2 and 3's interaction, it becomes the initial speed. Fair enough? All right. So let me move all this stuff out of the way. And now we'll start with our, I'm going to jump to this stage of our generic conservation of momentum solution, but now it's M2 V2 initial plus M3 V3 initial is M2 V2 final plus M3 V3 final. So this is now a interaction between object 2 and object 3. Now remember, initially here we have, well, we haven't defined, but it doesn't say that it doesn't say that the person is initially moving, the second person, so we assume that he's not. And because of the intricacies of this situation, which are, you got to imagine that the snowball gets totally, all of it sticks to the person, so they kind of have one combined, they kind of act as M2 plus M3, a combined system that now has some final velocity afterwards. All right, and we want to know, well, what the person's velocity is, but that's the velocity of the system. All right, so we say that the velocity is M2 V2 initial divided by oops, 2 plus 3. All right, so that's 0.045 kilograms moving at that 30 meters per second divided by our combined mass. When you get what you get. I get a 0.022 meters per second. So really, really slow, but if there's a perfectly frictionless situation, right, then this, that snowball hits this person, and then momentum of the snowball becomes the momentum of the snowball person system. The system's way more massive, so to conserve momentum moves way more slowly. Okay? Okay, here is a different kind of question. I wish that I had changed this a little bit to make this velocity of the combined thing that way, because I really should show you one with different directions, but here we are. So let's see, we got a railroad car that mass, we get that speed, it collides and couples with two other coupled railroad cars, each with the same mass, moving in the same direction at half that other one's speed. What's the speed of the three of them afterwards? Not too bad. And how much kinetic energy is lost? A little bit harder. So, well, let's just jump right into the general solution, shall we? Now, this is our initial case, right? Two kind of two objects, really three, but we can sort of call it two, can't we? Afterwards, the three objects. Well, I'm just going to do it like this. The three of them stick together and move with some speed vf. That means sticks together. Okay, so here's what I'm going to do. If we say that momentum is conserved, well, generically, m1, v1 initial plus m2, v2 initial, and 1, v1 final, m2, v2 final. Well, probably appropriate here to start talking about what different things are called, right? So, my m1 is called m. My m2 is 2m. All right. Now over here, maybe let's stick with the initial side. My v1 initial is called s. My v2 initial is called s over 2. And there's our plus. Now in the end, this is, well, really a couple ways to do it. One of them is to say that this is m1 at speed vf plus m2 at speed vf, which is the same as saying m1 plus m2 at vf. My m1 is m, my m2 is 2m, so really it's the same as saying 3m at vf. Fair enough? I would highly recommend, anytime things hit and stick, that as soon as you can, get to the system mass at final velocity style of expression. Okay? So I am gonna do a little movement of things, and there we are. Okay, so left side, let's do some algebra and simplify. Well, first off, this 2 and this 2 go. So we have m times s plus m times s is 3m times vf. We have a choice here, but when I see a common factor in every term, I always do, well, I don't always, but it's appropriate to divide those away. Notice on the left we have s plus s, that's 2s. On the right we're left with 3v final. So there's our answer for v final. 2/3 of s. Yeah, it's okay. Fair enough. Okay. Now the kinetic energy lost, and here's the deal. There are very special kinds of interactions where mechanical energy is conserved. Very special ones. But in most interactions, mechanical energy is not conserved. Should I say that? I should say the kinetic energy is not conserved. Well, for sure we know that in a case where things, like in this case, collide and come in contact and stick together, there's mechanical energy converted into sound. All right, there is also mechanical energy converted into probably thermal energy as surfaces heat up a little bit. When there are some uh, parts of objects that are deformed a little bit, we lose mechanical energy to that deformation. All right, so what can be asked sometimes commonly is how much kinetic energy is lost. All right, so what you really want to do here is look at or do an analysis of how much kinetic energy there was, and then do an analysis of how much kinetic energy there is, and compare them. Right? Do not set them equal because they're saying they're not equal. All right, so if we're looking for kinetic energy, we need expressions for kinetic energy. Now, in the beginning, there are two different objects moving at different speeds. We know what their speeds are, we know their characteristics, so we can write expressions for each of these. K initial, well, this one's kinetic energy is 1/2 m v squared. Yeah? The second one's is 1/2 m v squared. So let's simplify. This is not much to do here. 1/2 ms squared plus here I see 1/2 and a 2 I can divide away, and then we just have to be careful here. This is m. What now? This is m s squared over 2. I'm sorry, 4. Right? When we square this whole fraction, you got to square both parts. So here people get all sorts of screwy, but what I want you to recognize is this is 1/2 ms squared plus, well, the order in which we multiply or divide things doesn't matter. So here's another ms squared and a divided by 4, so I'm going to write that like that. Okay? Now, some people recognize that this is like a common factor to both of those terms. It's like saying, all right, we got a 3x and a 5x. Oh, these both have an x in them. Now, everyone knows here you just say 8x, right? But when we see things like this, people say, well, isn't that like 1/2 plus 1/4, and then there's m plus m and s squared plus s. People start to get a little screwy when things aren't just x's anymore. All right, but what I will encourage you to do is think of this. Well, I mean, the ms squared is kind of like our x over here. Oops, not sure. Kind of like that x over here. So what we're really doing is factoring out this ms squared. And in this term, there's a 1/2 multiplied by that. And in this term, there's a 1/4 multiplied by that. And then we just add the 1/2 and the 1/4. Or the 2/4 and the 1/4. So that's ms squared times 3/4. Or 3ms squared over 4. That's the initial kinetic energy. All right, so again, try to find that common factor. Keep it, right, like the common factor. Keep it, and then just add the coefficients. Right, add the coefficients. Okay, so that's the initial kinetic energy. Let's find the final kinetic energy. I'll go to green. Final kinetic energy, well, there's really one thing moving, and it's mass 3m. And what is its speed? Well, we found its speed from the previous problem. Its speed is 2s over 3. Don't forget to square. Let's simplify this. K final is 1/2 3m 4s squared over 9. Yeah? Well, I can do the 2 and the 4 and the 3 and the 9 and change this to, let's see, this is going to be 2ms squared over 3. You dig? We did that becomes a 2, that becomes a 3. Yeah? So that one was actually kind of easy if you treat this as a system, knowing its final speed from the previous example. And then just be careful when you square that you square all parts of that speed. All right, so here's what we have. We have a K initial 3/4 ms squared. We have a K final 2/3 ms squared. So how much kinetic energy was lost? Well, the difference. K lost is K initial minus K final, which is 3/4 ms squared minus 2/3 ms squared. And again, what we have is an extent. Why can I go no lower? I had to go to a whole new page for some reason. Anyway, so the difference, there's the difference. Well, look, once again, we have this common factor that we can pull out, right? So K lost is ms squared. Now, in this first term, we have 3/4 multiplied by that. And in the second term, we have 2/3 multiplied by that. And that minus just carries down. So then what's the difference in 3/4 or of 3/4 and 2/3? Well, now we got to go common denominator, 12ths, right? 9/12 minus 8/12. So our kinetic energy lost is ms squared times 1/12. Or perhaps 1/12 ms squared. Or perhaps ms squared over 12. Any of those are right. They're all equivalent. Okay? Okay. So take a little practice, for sure. And again, one of the things that we really didn't touch on in any of these problems, which is a bummer, is we didn't touch on things moving in different directions. So we got to make sure we'll get some more practice with those. But there's a couple of I hope, thorough solutions. All right? All right.